Hello everyone, I'm Amin, and I'm going to be presenting our work called ResQ, which is a system to enable SLO enforcement in the context of network function virtualization. This is a joint work with my great colleagues at Berkeley and Katerina at EPFL. There was an NFV session yesterday, so you probably by now, if you didn't know before, you know what NFV is. Just as a quick reminder, in one slide, I want to tell you what it is and how it differs from traditional way of building networks. Traditionally, networks are built out of fixed function hardware appliances, whereas with network function virtualization, these functions, which we refer to as network functions, are implemented in software and are multiplexed and run on a shared infrastructure, basically a pool of commodity servers. While it brings about a lot of good things, including flexibility and deploying and developing these functions, it brings about new challenges. One of the key challenges is that offering performance guarantees before was not easy. It's even harder now. And the crux of it, and why it is different than the fixed function hardware model, is that performance depends on neighbors' activity. So if you have functions co-located with other functions on the same box or sharing the same resources, they'll have different performance. And this, and in turn, is because of sharing a lot of resources that we have. So network resources, servers, resources inside the server, and down to processors, resources inside the processor. The deployment model we assume in this work is in line with what is commonly assumed for NFV deployments. It's a constricted model of resource sharing. It's not generally that you can run anything anywhere and let everyone share resources however they want. So just as highlighted, I mentioned three of those assumptions. So to begin with, we assume we have knobs and mechanisms for traffic isolation. So if we have independent flows of traffic, classes of traffic, there are QoS mechanisms in network and in the servers through NIC QoS mechanisms that enable us to isolate traffic so that we will not focus on solving that problem. Second is that we assume that independent NFs do not share the same core. So if you have NF from tenant 1, NF from tenant 2, we will never schedule them on the same core. And finally, what we will be addressing this for is sharing of processor resources, on-die processor resources that are not cores. And this is commonly referred to as on-core resources. That consists of I/O controller on the CPU die, memory controller, shared last level cache, and many other units on the processor. So a valid question to ask is that it's obvious that you can synthesize a workload for contention for these shared resources to matter. But realistically, with compute workloads being network functions, is it realistic that we see any degradation in performance if we start sharing on-core resources and not core resources? Just a reminder, virtual machine and containers, things like that. Even if they run on different cores of the same processor, they do not provide isolation. On the processor level, there are resources that are shared. So those alone are not sufficient for performance isolation. So it doesn't matter. To answer that, we run a series of experiments, very simple experiments. So we run a target network function alone on one core of the CPU. For this example, the network function just takes one core. We record the throughput and latency, T solo and latency solo. And we compare this throughput and latency with throughput and latency of consolidated runs. So each of those boxes on the right shows one experiment. So let's say a NAT box is the target NF. We run it with n other firewall boxes. In the second example, a NAT box run with WAN optimizers, and so on and so forth. So the question is, how far off is this minimum of TIs and the maximum of LIs compared to the solo run? This is the result. So for both throughput and latency for traffic consistent of small packets and large packets. For a wide range of network functions, we observe degradation. The degradation could be, for some NFs, they're not sensitive to resource. They're not sensitive to these resources being shared. They do not show much degradation, but there are many NFs for which one or more of these metrics start degrading. And the degradation could be up to around 45% for throughput and 25% for latency. So in conclusion, this is a real problem. We see a significant degradation with realistic traffic and realistic NFs, and not with synthetic workloads. There are two main approaches to offer SLOs. The first approach is what most of prior work does, and that is based on prediction. And then that's an indirect approach. So prediction along with contention over placement and scheduling. What it means basically is that you have a predictor that predicts the effects of resource contention and resource sharing by a collection of functions on the same box. The challenges that this brings about and a good work should handle is that accurate prediction is key. Why do we need accurate prediction? It is hard, but it's also important, because if we have an optimistic scheduler, if it tries to be quite close to the target degradation, it might violate its SLOs. On the other hand, if we have a conservative predictor, it may lead to inefficient resource packing and resource scheduling. The other thing, even if we have a good predictor, using it is algorithmically complex. And finally, let's assume we have a good predictor. Let's assume we nail the algorithmic part. The challenge we have at the end of the day is that if one of the tenants violates its SLOs because it deviates, it's under DDoS, there is no isolation between that NF or that function and the neighboring function. On the other hand, we have a very direct approach that is enabled very recently, I will talk about shortly, and that is based on direct isolation and neighbor-independent placement. So regardless of who your neighbor is, you can place a function wherever you want and get the same performance. Good thing, there is no need for prediction. It's algorithmically simpler, and it maintains isolation despite SLO violations. So you never affect your neighbors. And this is in part enabled by the emergence of resource isolation mechanisms in hardware, namely CPUs today. Our work, ResQ, builds on the latter mechanism. So it enforces SLOs for network functions by direct isolation. The rest of the talk has two parts. The first part, I will talk about direct performance isolation and how we achieve it. Second part is about performance SLO enforcement. And so basically how we use the direct enforcement knob, the direct performance isolation knob to enforce SLOs. So direct performance isolation. First, let's look at the hardware feature I talked about. In CPUs today, starting from Intel Broadwell CPUs, there's an umbrella feature called RDT, Resource Director Technology from Intel, that includes sub-features. One of the first sub-feature that emerged was cache allocation technology, which enables control over the shared last level cache. This resource in the middle. It's a very important resource because it's where lots of things are stitched together in a microprocessor today. So if there's I/O, it goes through LLC. If there's traffic to memory controller, it goes through LLC. For interprocessor traffic, it goes through LLC. So it was just natural for this to be the first feature that makes it to the market. How it works is rather simple. You classify cores, VMs, threads into some classes, cache classes, and then assign parts of last level cache to these classes. What I am showing here is non-overlapping allocations, but allocations could be overlapping. For full isolation for this work, I'm assuming non-overlapping allocations. So the natural question that happens here is whether CAT and LLC isolation is sufficient to ensure NF performance isolation. For a while, I personally and our colleagues thought that this is the case. But there are many reasons to believe that. There's prior work suggesting that, and naturally, you're inclined for many reasons to believe that's the case. But it is not. And more interestingly, the first experiments we ran in the NFV context are with the small packets. With the small packets, we achieve a very good level of isolation, up to 3% isolation, just by isolating the last level cache. But when we went with large packets, we have observed up to 15% degradation. And this is quite counterintuitive because the small packet traffic is more resource intensive. What we observed is a high memory utilization. Again, this is a counterintuitive because in general, we expect network functions to not have that much footprint, memory traffic footprint, because of the high packet rates they have and the closed loop nature they have. Moreover, another counterintuitive thing we observed is that the network function LLC miss rate, so the last level cache miss rate, we observed for a small packet and large packet traffic was pretty much the same. So what is happening is I/O related. So we have a high I/O related memory traffic due to LLC misses for I/O. And with that, the problem is with I/O, and specifically DDI/O, and how it operates and how the software uses that feature. And we coined the term the Leaky DMA problem to refer to this problem. So first, how does I/O work at a high level? So starting from Sandy Bridge, the Intel processors do DMA. The NICs and other I/O devices, when they do DMA, the content will be allocated directly in the last level cache. And the space that is used for that allocation is by default 10% of the cache, somewhere in the middle of the LLC. So what happens is that when we have large packets, the buffer requirements for small packets and large packets, there is a 13x difference between the two, 13x difference between the two. And they start contending very, very heavily for this space, both on the RX path and the TX path. Imagine your NF is done with packet processing. It leaves the packets there in the LLC until DMA picks it up and emits it. So even if your NF thinks it is done with processing, until the packet leaves the machine, it's not, gets to the NIC, it's not done. So another thing to note is that CAT does not apply here. CAT does not apply to I/O. So this LLC sharing for I/O is at the core of the problem. The solution, once you know the problem, is rather straightforward. There are a range of solutions you can take. One is limiting the number of packets on the fly using mechanisms like buffer sizing. So never let more than n packets in the system at the same time aggregate on the same processor. And with that, let's look at the results. So the before case is up there, up to 45% degradation. For throughput, 25% for latency. After, it drops down to less than 3% for both throughput and latency. So this is a LLC isolation along with correct buffer sizing or handling the leaky DMA problem sufficiently well ensures that for network functions, for this specific workload, we have a highly accurate mechanism for performance isolation. So the second part of the talk is about how to do SLO enforcement using this knob. So in ResQ, we have two types of SLOs. First one is reserved SLOs, which basically do a static allocation. As input, you pass the NF, expected configuration, and expected traffic profile, and you specify the target throughput and latency you want. And the other one is on-demand SLOs, for which we do dynamic allocation of resources. as the input is simply NF. You don't need to specify your expected configuration or traffic profile, and just specify your target latency. And the system on demand tries to see if the latency target is violated and boosts up more, gives you more resources to meet that demand. In the rest of the talk, I'll focus on the reserved SLOs. So the very first part of the ResQ process is admission. Upon submission of an SLO term for service, we profile the NF. The NF could be an NF chain or collectively what the customer wants as part of a single SLO term. So we profile it to construct a performance model. That performance model says what the throughput and latency is as a function of cache allocation and as a function of input packet rate. This process, we have made it fast and scalable. By fast, I mean it's in the fast path of the admission process. So if it takes 10 minutes, the admission will take 10 minutes. We don't want that. And it's scalable. It means that if we grow with size, we can add more profilers that are independent from one another, and we can scale that process. The second part is fast greedy admission. So with that, it's simply means that if we don't have enough resources to admit it, deny admission. If we do have enough resources, compute the number of instances we need for this specific SLO term. And for each of the instances, compute which core you'll be placing it on, or which cores you'll be placing it on, and the LLC allocation per instance. The greedy allocation will show that it's pretty good, but it's not supposed to be optimal. The optimal scheduling, we formulated as a mixed integer linear program. It's slow compared to the greedy allocation and greedy admission. So it will. So what we do is we don't put it in the admission path, in the fast path of the process. We run it in the background, and if necessary, if the gap and the gains by rearranging NFs to move to this more optimal schedule is sufficient, we'll rearrange NFs to go to this new schedule. It's practical for small clusters of, let's say, 40 servers or around that number. And it says mostly takes seconds, up to minutes. For larger clusters, we can divide and conquer and have different solvers for different pools of servers, trading sum of optimality for scaling. So resource efficiency. This is the slide that is trying to sum up what gains we have and what we'll lose by having this level of isolation and SLO enforcement. So for that, we generate around 200 sample SLO terms, and they're all SLO terms. There are three classes of such SLOs we generate. The first class is insensitive. All NFs are insensitive to cache allocation. To resource sharing. Combination, we have a combination of the two. We have combination of insensitive and sensitive ones, and sensitive is all sensitive NFs. And there are four schemes we are comparing. First one is optimal scheduling with ResQ. Second one is the greediest scheduling. Third one is dynamic scheduling, on-demand scheduling with no isolation. So this is prior work. And lastly, we have prediction-based approach, where we have a predictor, we use it to enforce SLOs. So insensitive ones, let's get it out of the way. It doesn't matter, whatever you use. So with the same resources, we'll meet the demand. For the combination ones, you'll start seeing a growing gap between the solutions. And that gap grows significantly when we go with more aggressive workloads. So let's let me walk you through the results. So greedy and optimal, the gap in our sample is around 18.5%. So that's what we lose by doing greedy allocation. And that's pretty good, actually. With dynamic, it's fair to compare with the greedy allocation. There is a cost to hard partitioning resources. There's a cost to hard isolation. But the cost in our sample workload is less than 3%. So, and that is only in one case. So it takes one more server to do hard partition of resources. And finally, The prediction-based approach is highly inefficient, especially in the last case, because the predictor it uses is highly conservative. So in conclusion, ResQ achieves better accuracy and efficiency compared to prior work. And this is despite using very simple heuristics and algorithms. So there is very little complexity in the algorithms we use and novelty there. But this is enabled by direct performance isolation. There is plenty of room for improvement with software mechanisms to complement the hardware isolation. For example, there is a great work at HPCA this year called K-part that shows how we can achieve better granularity of sharing, and that can complement this work. And finally, the code is available on GitHub, and this is generally useful for NFV experimentation. With that, I thank you and happy to take questions.
Any questions? Okay, so while people are rounding up their thoughts, let me start. So you mentioned that you were reducing basically the ring buffers on the NICs to make sure that you don't have the large packet problem, right? Mm-hmm. So obviously with smaller ring buffers, you'll reduce performance for small packet sizes. So how do you choose the right number there, and do you do it dynamically or?
So you don't actually need, even though in our experimental setup we actually reduce the ring buffer size, you don't need to reduce the ring buffer size. You only need to reduce the number of DMA buffers in software, right, so that DMA doesn't happen. So packets are still there. It's just where the queuing happens. We don't want the packets to be brought in the CPU. They are queued up on the NIC.
But at the end of the day, it's the same, right? You'll start dropping packets somewhere, and you'll basically drop.
So we believe, let's say, 2,000 packets, or the ring size of 2,000 packets or 4,000 packets is plenty on the NIC to not hit that problem with the small packets.
Thank you. Yeah, and thank you for the good work. And so my question is how the cache allocation isolation is different from in terms of performance from user space isolation using something like C group and network namespaces and things like that.
So C groups and network namespaces do not provide you with isolation at that level. Interestingly, there was a C groups patch for cache allocation. They moved to a different scheme, but underlying system, there is no mechanism that ensures cache isolation. So the results I showed is with perfect isolation from the C groups standpoint pre-cat. So with that, we'll see those results. So it's 45% degradation in throughput, 25% degradation in latency, and that is with perfect isolation from your standard isolation standpoint. And it makes sense.
So will the next speaker come up and set up their laptop, please? And then we have one more question.
Hi, this is Yorgos. Great talk. So I have two questions. First one, do you use DPDK? And if so, how can you explicitly control the slice allocation in the LLC? And the second question is, what kind of predictor did you use in the last graph that you showed?
So the NFs, we use a wide range of NFs. Some of them are DPDK-based, some of them are netmap-based. So it varies from case to case. So each of those bars is independent. The second question, how do we control LLC allocation? So for that, NFs are scheduled on different cores. We just put that core in a cache class. You just put the TID or process ID of the process in a cache class and specify how much cache that process needs. That's it. I mean, from the interface perspective, that's how it looks like. Yes, so the deployment pins it to the core. The scheduling puts the core in a class, a cache class.
Perhaps you can take this offline. Let's thank Amin again. Thank you.